So let's ask, what is the limit as t approaches 0 of this function? And this function is going to be, let's say, t plus 1 and 3t squared and sine of t over t. So just like derivatives or antiderivatives, whenever we do limits, we're going to do it one component at a time. So like looking at the x component, what's the limit as t approaches 0? 1. Looking at the y component, what's the limit as t approaches 0? 0. And then what about the z component? What's the limit as t approaches 0?
1.
It's 1, yeah. And so, like, these two were easy limits. I gave you a hard one for the z component, like sine of t over t. So if you just plug in t equals 0, you have sine of 0 over 0, which is a 0 over 0. It's undefined. You could use like L'Hopital's rule, right? If you remember that. And we take the derivative of the top, the derivative of the bottom, and we get cosine of t over 1. So cosine of 0 over 1 is just 1. I think that's how you do it. When I say I think that's how you do it, I know that's how you do it. So even if just one of your components doesn't have a limit, like if I ask you what's the limit as t approaches 1 of this, okay, the limit of my y component is 3. The limit of my z component would be 4. But the limit as t approaches 1 of 1 over t minus 1. Right, plug that in, that's 1 over 0. If you were approaching this limit from the right side, that would go up to positive infinity. If you're approaching this limit from the left side, that would go down towards negative infinity. So we're talking about a vertical asymptote where there's not a limit. It's not continuous there. And it's not a removable discontinuity either. And so here, for this pole, we would say that it is undefined. And so if any component of the limit is undefined, you would say that this whole limit of this whole vector valued function is undefined at the point t equals 1. So if any one of the components is undefined, we just say the whole limit of the vector valued function is undefined there.
Is this an example of singularity, or is it different?
Yeah, like that's what you'd call a singularity, right? Or are you thinking about something else?
No, because I remember this. It was back in high school. There was a doctorate of mathematics. It was talking about differential geometry and singularity and all that. And I'm like, what is singularity is doing? And he explained the applied part in real world in engineering, like singularities and antennas and all that. And he said he had to find some limits, and whenever it was defined, we would call it a singularity.
Okay, so yeah, my understanding of the word singularity as it applies in just like the calculus sense is kind of mostly the same-ish as like a asymptote or a pole or something like this, right? So if you hear somebody use the word singularity and we're just talking about this in the context of just functions, then normally we say singularity is an asymptote. So like I was saying in this example, y equals 1 over 1 minus x. Like that point at x equals 1 is what we would call the singularity of that function. So it's just another one of those vocabulary words. Now, in the context of like differential geometry, like big application of differential geometry is obviously Einstein's general theory of relativity. And so in the context of relativity, when we talk about a singularity, we're talking about either a black hole or the Big Bang. The reason that we call those singularities is because at a black hole, the gravitational pull sort of becomes infinite whenever you look at the equations, right? Like you take the limit of whatever as you approach the singularity in the center of the black hole, and it sort of does this to gravity or density. And same thing with the Big Bang. The Big Bang is a point where we sort of had infinite density. You know, if we assume the universe is infinitely large, then the Big Bang would have had infinite density at that point. So if you were to rewind, if you were to like sort of rewind time back to this point, you know, if the x-axis is my time axis, my y-axis is like the density, you know, then the density of the universe would sort of do this. So that's why we call it a singularity.
Like we don't have so much information about that particular point, right? Like everything is extreme, like infinity or too small or too big. It's like
yeah. Yeah. Okay.
Like, can you visualize the parametric equation you gave us? The parametric, the vector value, yeah, this one. Can you visualize it?
Yeah.
To see the.
Okay.
The level.
Let's try that. Here we go. So 1 over t minus 1. Okay. Let's see. 1 over t minus 1, 3t, 4t squared. Okay, so this is exactly what I wrote down. And what is going to infinity here should be my x-axis, and I don't really know which one is x. I guess the blue is my z value. No. Let me think about this.
The green is the x-axis.
Okay, so blue is my z-axis, green is my y-axis, red is my x-axis. The reason I say this is because from this view it looks like a parabola, and if I think of just z as a function of y, I could write that z equals 4/3 y squared by eliminating the parameter. So I think that blue is z and green is y. And so at the point where y is equal to 3, we should have a singularity in my x. And so yeah, at the point where, okay, so now green is y, red is x, right? And so sure enough, at the point where my y value is 3, then along my red x-axis, it goes to positive infinity or negative infinity. Yeah, okay. There we go.
Like two portions and then combined, you have a parabola.
Yeah, it's kind of neat.
Yeah.
But anyways, that's why we say the limit doesn't exist there. It's because there's not like a point where these look like they would link up. If we tried, you know, instead of 1 over t minus 1, what if we did sine of t over t, right? sine of t over t. So still at the point where t is equal to 0, we should have a discontinuity, right? Or when y is equal to 0, we should have a discontinuity. But it's a removable discontinuity, right? So like, technically the curve doesn't exist right there, but we could remove that discontinuity just by filling it in, right? Just by arbitrarily saying that when t is 0, then the x value is 1. And then we could just fill in the curve right there. So that does have a limit at that point, at that value of t. Okay. Any other math questions about this?
The antiderivative that satisfies like an initial condition. That's like
Okay. Can you give me a problem number?
I guess 55. What is it?
Is it 12.1 or 12.2? 12.2, 55, okay. Okay. So, find an antiderivative that satisfies initial conditions. Okay, so I have r double prime of t is equal to negative 32j. And r prime of 0 is equal to 600 square root 3 I plus 600j, and r of 0 is 0. Okay. And what we want is we want a formula for r of t that satisfies all of these things at the same time. So if I start with r double prime of t, right, and then I take the antiderivative of this, then I should get r prime of t plus or minus some kind of constant, and that's a constant vector, right? I can add a constant to any of the x, y, z components. So, taking the antiderivative of minus 32j, of course that is a constant, so I just have to add a little t to it, and so this is going to be some constant, we'll call it c1, times I plus, well, negative 32, negative 32t plus c2 times j plus some constant times k. But this, everything that I wrote here, whenever I plug in t equals 0, then this has to be equal to this, right? Because if I take r prime at 0, then I need to be able to get 600 root 3i plus 600j plus 0k. And so just by looking at this, I can tell that my value for C1 has to be what? 600 square root 3. And my value for C2 has to be
600.
perfect, 600. Because t is 0, so that negative 32 times 0 just goes to 0. And then C3 is what? 0. Okay. So that means r prime of t is going to be 600 root 3I plus negative 32t plus 600j plus 0k. So it's just that. The next thing we would do is say, well, let me take the antiderivative of r prime of t with respect to t, so I can find an r of t. And so my antiderivative here is going to be 600 square root 3 times t plus some constant, we'll call it c4, times I, plus, for j, I'm going to have negative 16t squared plus 600t plus c5 times j plus, we'll call it c6 times k. But here, whenever I set t equal to 0, what I need for r of 0 is 0. So if I set t equal to 0, and I want my r of t to be 0, in other words, I want r of 0 to be 0, that means that this constant c4 has to be what? 0. And that means this constant c5 has to be 0. Because if I set t equal to 0, I need everything to be 0. And then lastly, my constant c6 has to be 0. Okay. So that means r of t, that satisfies those conditions I was given, is 600 root 3 t I plus negative 16t squared plus 600 t j plus 0k. That was a good question. To kind of recap, what those initial conditions are is it says when t is equal to 0, here are some specific values for the first derivative and the function r of t itself, right? So give us r prime of 0 and r of 0. What those initial conditions are doing for us is they are specifying exactly what those constants of integration are. What I mean by constant of integration is like you take the antiderivative, so you can add or subtract any constant. We don't know what those are, but you can actually use the initial conditions as clues to narrow down what those constants have to be each time you take an antiderivative. Yeah.